Hello everyone and welcome back to Ronnie Explains. So in today's session, I'm going to take you through the process of designing a circuit of a parity generator, and we are going to work in 4 bits. So parity generator is a machine that is able to detect errors. We have two types of parity generators. We have even parity generator and odd parity generator. So if it's an even parity generator, for example, and we have bits like 0, 0, 1, and it should be an even parity generator. So 001 is the input state. Then what is going to happen is that if this column here, for instance, represent the input state, then the output, this other side, is gonna be 1. For even parity generator, it adds 1 if the number of ones in the input is odd. So if it adds 1 here, then the number becomes even. So if this even uh, this even sequence of bits is finally received at the final end during checking of the transmitted data, and it is determined that the number of ones are even, then it will not detect any error. All right, so what I'm going to do is I'm going to work in 4 bits, and therefore here I am going to have numbers from 0 to 15. So the whole of this, I will drag it down like this. One more number, 15. Then here I will have some sequence of some series of zeros up to there. Then from 8, I'll have ones like this up to 15. So I'll copy the some of the series of zeros and ones just to avoid a lot of typing. Then I'll also take them in twos like this. Then finally, I'll take them in pairs of ones. And we are going to have here this data here as inputs, and I will label them A, B, C, and D. This side here, these ones are the input values. So I'll simply merge these cells here and call that input. Just do some center alignment, and here I have the output. My output will be represented by letter Y. So this is what I am gonna do for this parity generator. So from here, I'm going to check, because I'm creating an even parity generator, I'm going to check the numbers of ones that I have. Here I have 0 numbers of ones, therefore this point here I will simply have 0. Then for this state 1 here I have 1. So that one is an odd number, and I will add another one for it to be an even number. So here we'll have 1. Then in this column here, I have 1 here. So therefore this other side I also have 1 for them to be even pair. Then here I have 2 of them. So this other side I'll have 0 because 2 is already an even number. Here I will have 1 for it to be an even pair, and down here I'll have 0 because we already have 2 ones, so that's already an even number. Down here I have 2 of them, so then here I'll have 0. Then here I have 3 of them, so I'll add 1 for them to become 4. Then down here I will add 1 for them to become an even pair. Here I'll put 0 because 2 is already an even number. Down here I will put 0 because 2 here is already an even number. Here I will put 1 for them to become 4 of them, which is even. Then here I will put 0 because 2 of them is already an even number. Down here I'll also add 1 for them to become 4, which is even. Then down here I also add 1, so there will be 4 of them, which is even. And finally here I'll put 0 because 4 is already an even number. This outputs here for me to distinguish between outputs and inputs. So this one I'll just give it a separate color, maybe that color will do. Then here I will also give it a different color, maybe color green. These are the states, so I won't care much about them. Now in this other side, what I'm going to do is I'm going to prepare a kernel map for these output values, and as you can see we are working in 4 bits from 0 to 15, and that is why at this point my kernel map is going to be a 4 variable kernel map. So that one will do. I'll just create some borders here and merge some few cells. So I'll merge that, then I'll merge that, I'll merge this, and then I'll also merge this, like that. I'll call this one A, then I'll call this B, call this C, and call this here D. Now this values A, B, C, and D, I'll just bolden them and then do some alignment. A will be aligned towards the right, like that. D and C will be aligned at the center. That's how it is. Then I'm going to feed in these output values. For example, this is 0, 1, 1, 0 up to here. So here I'm going to have 0, 1, 1, 0. Then on this side, I am going to have 1, 0, 0, 1. So here I'll have 1, 0, 0, 1. Then here I will have 1, 0, 0, 1 again. So this one will be 1, 0, 0, 1. Then this last one is gonna be 0, 1, 1, 0. So this is 0, 1, 1, 0. I'll just center all my input bits like that. Then begin forming the groups. Now, one thing that I want you to note is that before you can even begin forming any group here, then you realize that we are having this as a checkerboard. What you are going to have here in short is an expression of XOR gates. So the value of Y is simply going to be A XOR B XOR C XOR D. That is how the expression is going to be. If you want to verify this, then you can go on and make these groups, like make groups for every single one of this, and then simplify your logic expression. Finally, you'll simply end up with this one. And in that process of simplification, you remember to use De Morgan's law. It will be very easy and helpful to help you come up with this final expression. So what I'm going to do now that I have this, I'm simply going to prepare my parity generator circuit. So I'll come and launch my software, Hades.jar, do some few setups, instant layers and port labels to be checked. Then I will set up my magnetic grid to 1/8 inch. I'll create some input, so I/O I-pin switch, then I put 4 of them because I'm having 4 input data. In other words, I'm working in 4 bits. So I'll have 1, 2, 3, and 4. I'll just give them the names. So the first one is called A, the next one here is called B, the next one here is called C, and the final one is D. Then I will just combine this using XOR gate. So A and B here, I'm going to create gates, but I am gonna use XOR. So XOR gate, it's a 2 input, so I'm going to use this. So I'll paste it here twice. I'll have this and also the one that will be combining the last two values. Then the last one will also be combining this, and therefore I'll put it somewhere here. So this here is gonna be here, and this is also gonna be here like this. Then I'll have this, and I'll also have this. Then this is gonna be combined with the last XOR gate. Now, the output of this circuit is going to be this other side, and we're going to represent it in form of an LED. So I'll create IO, then output LED, and I'll put it somewhere here. So then I will combine them like that. So this is what I have. Control plus F to view it in full mode. Then we can try to test it if it's giving the correct results. And before I can test it, so I can name some few things here. So this first one, so I will name this as A XOR B, and then I'll name this down here as C XOR D. Then here, the name of this will be A XOR B XOR C XOR D. So that is what I'm having. I can just do some few checks. Put all this off, then start with binary 1. For that, I'll just have to reduce this window a bit so that I can check against the values of my truth table. Then on this other side, Control plus F. So in the first case here, we have 0, 0, 0, 0. So if I have all of them as 0, 0, 0, 0, you can clearly see that the output value here is off. And let me also change the name of this to Y because it's the output. So the value of Y is also 0. In the second one, it's 0, 0, 0, 1. The value of Y is supposed to be 1. So 0, 0, 0, 1, value of Y is 1. In the third one, it is 0, 0, 1, 0. And if this is 0, 0, 1, 0, then this also 1. So value of Y is 1. In the fourth one, 0, 0, 1, 1. So this other side, we have 0. So 0, 0, 1, 1. So 0, 0, 1, 1, you can see it's 0. That is this. The next one is 0, 1, 0, 0. The output should be 1. 0, 1, 0, 0. The output is 1. The next is 0, 1, 0, 1. The output is 0. 0, 1, 0, 1. The output is 0. The next is 0, 1, 1, 0. The output is 0. 0, 1, 1, 0. The output is 0. The next is 0, 1, 1, 1. The output is 1. So 0, 1, 1, 1. The output is 1. The next one we have 1, 0, 0, 0. The output is 1. So 1, 0, 0, 0. The output is 1. Then the next one we have 1, 0, 0, 1. The output is 0. That is 1, 0, 0, 1. The output is 0. Then we have 1, 0, 1, 0. The output is 0. So that's 1, 0, 1, 0. The output becomes 0. Then we have 1, 0, 1, 1. The output is 1. So 1, 0, 1, 1. The output is 1. Then 1, 1, 0, 0. The output is 0. So 1, 1, 0, 0. The output is 0. And then we have 1, 1, 0, 1. The output is 1. Like that. Then we have 1, 1, 1, 0. The output is 1. Then finally we have 1, 1, 1, 1. The output is 0. So that is how a parity generator works. And you can implement such a circuit also by just creating some few sub designs and checking at the final end to see how it really works in real life if you are entering these values as decimal numbers, and that is what I'm going to do next. So this side, I will come here, Control plus F to view it in full screen mode. Then I will come to edit and create a symbol, and then I will come to file, then I just click new. Though it prompts me to save what I have already, so I'll just come here and say save, and then I will save it in its own new folder. So I'll create a new folder here and name this one here as a parity checker. Then I say open. So under this, I will name this one here as parity. Then I'll save it and it opens this new one. So I'll also have to check my instant labels and port labels. All of them are okay. Then I come to my edit and my view and set my magnetic grid to 1/8. So right here, I'll right click, then create a sub design, and I'm going to create a sub design for this one here. I'm going to connect it to an hexadecimal switch. So I'll come here and create IO, then I will say hexadecimal switch. I'll put it here, and this other side I will have an LED that will be displaying for me the output. Just move it a bit and put it somewhere there. Then I will connect all these inputs and outputs like that, and also connect this LED here. So basically this is how it looks like. So if you want to implement this to see how it is working now in real life as you work with decimal numbers, then you can cross-check against the truth table that we are having here. So right now, so this other side, Control plus F, and then name this as Y. It's already named. If I am at 0 here, then this is also 0. So you can clearly see that if 0, then this is 0. Then if you go to 1, then this here becomes 1. So if you go to 2, then it's also 1, because here we had only one of the ones. So then we need this extra one for it to become a parity. If you go down here to 3, then it becomes 0 here. If you go to 4, it becomes 1. If you go to 5, it becomes 0. We are here. If you go to 6, it becomes 0. If you go to 7, it becomes 1. If you go to 8, you will have 1. If you go to 9, then it becomes 0. If you go to 10, it becomes 0. If you go to 11, here it becomes 1. If you go to 12, then you have 0. If you are at 13, it becomes 1. If you are 14, becomes 1. And finally, if you are at 15, it becomes 0. So that is how a parity circuit works. If you found this helpful, please give it a thumbs up and remember to subscribe for more upcoming contents. Thank you for your time.